everyone. I'm Elizabeth Jaramillo. I'm going to present the work that's being done on MICA, which is a microfluidic Icy-World chemistry analyzer. This is a collaboration between a couple of different NASA centers, NASA Ames, Jet Propulsion Labs, Tufts University. Tony Rico is the PI on it. And so MICA is basically a combination between the heritage of the Phoenix Wet Chemistry Labs, which flew and did some experiments on Mars back in 2008, and the work that's been done with microfluidics on small satellites through Ames. And together we're combining these into basically a smaller version of the Phoenix Wet Chemistry Labs that might be useful on a Europa lander potential mission. So the Europa lander science definition team report came out with, of course, several different key science goals that they were interested in, and we believe that the MICA instrument that we're building, while not necessarily obviously going to address these, it does have a very important role in them. And the primary measurements that MICA is going to make are inorganic measurements, which is a little bit different from what a lot of other people are talking about here today. It's an electrochemistry array that uses ion-selective electrodes, cyclical attachmetry, and chronopotentiometry. And where it fits in this science definition team report is looking at characterizing the inorganic environment, characterizing the sort of sources for energy that might be fueling these potential life forms, looking at the habitability of the surface, and just characterizing the chemical matrix in which the measurements will be taken. And so all of this sort of stems from the Phoenix lander. And so for those of you who maybe don't think about the Phoenix lander as often as some of us do, I want to remind you exactly what the wet chemistry labs are and why they're actually a really great stepping stone for the Europa lander. So in 2008, the Phoenix lander landed on the northern plains of Mars, and its mission was to assess the habitability of that site. And it did that with a lot of different tools. One of this was this microscopy, electrochemistry, and conductivity analyzer, MICA. And what MICA did was it had, as part of it, a series of 4 cells, which were the wet chemistry labs. And they were these electrochemical sensor arrays. They included a suite of ion-selective electrodes, conductivity probes, they sensed pH, oxidation reduction potential, and different oxidants in the soil. And this was really the first time that on Mars we were able to characterize the regolith in terms of these soluble species, which was very important. And in addition to having the success of actually measuring the primary cations that were in the soil and really giving us a context for that, it measured pH for the first time, and it detected perchlorate in the surface for the first time. And this was a really, really, really important contribution to how we understand Mars. So before this, we had always expected there to be organic molecules, and we'd go and we'd measure, and they weren't there, and we were all like, what is happening? And so when Phoenix showed up and they actually measured what was in the soil, and they measured what was in the matrix of the sample that they were trying to detect these organics in, they found this molecule called perchlorate. And perchlorate is interesting because if you heat it up in the presence of organics, what you get are a bunch of combusted organics, and you don't actually see what you wanted to see. So, since then, curiosity has then confirmed the presence of organic with this oxygen evolution peak. So when perchlorate degrades when you heat it up, it has this oxygen evolution peak, and it explains why we were really, for a long time, only getting these very small chlorinated organics. And it wasn't until very recently that we started to detect other things where we could search in environments that maybe perchlorate wasn't as abundant. And what I'm trying to emphasize here is the importance of measuring even this inorganic matrix before you start doing these incredibly complicated, awesome techniques that can maybe detect really low levels of organics and all of that. But if you don't understand your chemical matrix at the base level, then you could be missing something very obvious. And now you've wasted all of this time and energy because you just simply didn't test your matrix. And this is really a first step in any basic laboratory analysis. Test your pH, test what's in there. And so we know that we did a really excellent job on Mars, but there are different challenges for going forward on Europa. And so we've been developing these sensors to test them to make sure that they will be robust enough to handle the environments that we expect on Europa. And the first of those tests was the radiation dose. So the radiation on Europa is much larger than the radiation on Mars, and so we've been testing at this 300 kilorad total ionization dose because the molecules that do sort of the heavy lifting in an ion-selective electrode are actually small organic molecules. And so one of our concerns was that if they couldn't handle the higher radiation, that there would be a problem. And so we did some measurements, we calibrated them, and we compared them before and after this 300 kilorad total radiation dose, and we found that at least for the ones that we've tested so far, there doesn't really seem to be a loss of performance. So it looks like that high radiation environment doesn't seem to be going to be too much of a problem for at least these potentially these organic molecules that we put in our membranes. The second is the lifetime. So Mars is a lot closer than Europa. And so if we're looking at a 10-year flight mission, we just wanted to make sure that these electrodes would still function when we got there. And this was one of the great things about using a heritage technology, is we actually had an original flight spare beaker that back in 2007 they sealed up, put in a freezer, and forgot about for 10 years. And then when we said, well, would this work if we got to Europa in 10 years? It was very easy to test. We just opened up the beaker and we did the calibration again. And you can see before and after, the calibration, the sensitivity hasn't really changed over time. So they definitely do have a demonstrated actual 10-year survivability, which was pretty exciting for us to learn. And then the next thing that we wanted to know is, the original Wickel beakers used 25 milliliters of water. And that's a lot of water for Europa. And so we wanted to make sure that these would still function if we reduced that sample volume onto the microliter level. So we took the original form factor of the Wickel electrodes and we put them into a sort of microfluidic channel. So this is 14 electrodes in a total channel volume of 100 microliters. And we tested to see whether or not the performance changed going from a beaker with a large volume to this manifold with a small volume. And as you can tell, the performance actually stays pretty good. And Navita had a poster on, Monday, about that. And I'm sure it's still up if you are interested, or you can find her and chat about it. And she's been doing more work testing the different components to make sure that these manifolds still hold up. And there were, going forward, it's nice to know that these heritage kind of electrodes actually do function and they would be useful on Europa, and we could still get the same kind of excellent science return that we got from Phoenix using them. But we wanted to make sure that we weren't missing anything. So it's been a while since Phoenix, and there have been amazing technology advances since then. And so we sort of started looking at what the next generation of these ion selective electrodes looks like. And so we started comparing the heritage Wickel ones, which are here, to these solid contact ones to see if there would be a benefit in maybe sacrificing a little TRL to get some benefit later on, or whether or not it's better just to stick with the heritage. And so what we're mainly comparing here is the original heritage design. It uses a hydrogel inner filling solution in order to do its main transduction from an ionic signal to an electronic one. And while we know it can survive 10 years of storage, and we've done some dry storage testing, which also kind of confirms that we can bring them back to life after drying them out, we wanted to know whether or not there would be benefit in eliminating that. One of the benefits to eliminating that, aside from just potentially adding stability and survivability, would be that we can reduce the size. So this 6 millimeter size is kind of the limit if you're using that hydrogel. But by getting rid of it and using a carbon-based material, which uses a capacitive transduction mechanism instead of a redox-based one, we're able to get it down to 2 millimeters, so we could possibly fit more of them into a smaller array. And we've been developing these, really there's been a lot of iterations of developing these solid contact ones since the original Phoenix mission, and this is sort of the most recent one. So we have this 2 millimeter diameter using a graphene oxide carbon nanotube based transduction level, and we've sort of are currently testing it in this small form factor microfluidic array that includes calibration reservoirs and things of that nature, and conductivity, and testing it in this manner to see how it performs. And so far, it's performing just as well as the original heritage ones, which is excellent. We were also wanted to address some of the ions that we didn't actually measure when we were on Phoenix. IACs are really excellent at cations, and then things get a little fuzzier when you go to anions. And so while we were able to detect perchlorate, there are interferences, and detecting perchlorate meant we couldn't detect nitrate. And so we've been developing techniques using the same types of electronics and electrodes that were in the original one. We've been just sort of developing methods that would allow us to tailor that to detect other things. And so here's an example of some CV, which was on board the original Phoenix, using a silver electrode to detect nitrate. And you can see that the peak here varies with concentration, and you can actually measure your nitrate based on that. And we did a similar thing with sulfate and a lead electrode, where you can see that we can vary the concentration and get some potentially quantifying information about these anions that might be swamped by other signals in the ISEs. And so we've taken all of these wonderful developments for the Wickel heritage electrochemistry array, and we're sort of coupling it with the knowledge at NASA Ames with their microfluidics. So they've been doing these small satellite microfluidic devices for years, and I'm not going to talk too much about that because someone else can talk about it later if they feel like it. But we sort of brought these together and put it in this splice, which was talked about. It was funded under Cold Tech funding. I think Leslie talked about it on Tuesday, I believe. And this was sort of built in. It has these connections where it can integrate with this M-Wickel or these sort of microfluidic Wickel devices that we've been building. So we've been sort of testing it like that for a while, and then this all comes together eventually, and all of this knowledge and experience and this sort of heritage and high TRL work that we've been doing comes together in these actual proposed MICA systems. So we have a sealing door and a sample handling that's being developed by Honeybee that'll allow us to have meet the requirements that we need for that. We have our calibrations, our water reservoir, our electrochemical sensor right here, a series of pumps and valves, all of them. And all of these are meant to fit into a design that is about 10 centimeters by 17 by 11 and a half, and it's basically going to fit into one of these smaller sections of the proposed Europa lander. And so this is the current CAD design that we're working up, and we're actually getting printed, I don't want to say as we speak, but sometime in the not too distant future, for integration and testing of all of these final, or these initial designs that we've been doing. And so with that, I just want to run through these conclusions real quick. So we have these electrochemistry measurements that are really well suited to address things like habitability and sample site characterization, which is incredibly important when you're going to a place for the first time to do sort of complicated measurements. And it really incorporates a lot of really high TRL flight heritage devices, which makes it a really promising technology, and has been built off of funding from Coltex and things like that have been basically bringing all of this together since the start of it, and that we're at the stage where we're about to actually integrate all of these things and test them finally. So with that, I think if anyone has any questions.
Time for a question? Anyone?
Question. I was really intrigued by your use of the Phoenix parts. Was there anything else that you cannibalized that stood the test of time?
From Phoenix, well, yeah, so the spare flight beakers, it's funny, that box sits in the freezer for a while and it takes up a lot of space and then becomes very useful in that respect. If there's anything else from them that we're using specifically from Phoenix, I'm not sure, because that was really optimized for taking soil and mixing it with water, right? And here we're expecting to be able to sort of maybe melt our sample, and we don't need to do as much of the mixing. So from there we have a few tweaks, which is the microfluidics part of it, but yeah.
Cool, nice work.